Okay, let's talk about modeling and optimization. This is lesson 4.4, and we're going to look at two more examples. Example 3 is fabricating a box. Let's say we have an open top box. We're going to make it by cutting congruent squares of side length X from the corners of a 20 by 25 inch sheet of tin, and then we're going to bend up the sides. We want to know how large the square should be for the box to hold as much as possible, and what's the resulting maximum volume. If we go along with our idea of understanding the problem first. So I drew this nice box. It's a 20 by 25 sheet of tin, and we're going to cut out sides of side length X from each corner. Well, if we do that, what we'll have left when we fold up these sides, this is the side of the box then, and this will be the base of the box. And when we fold these sides up, what we're going to have here for this length is 25 minus 2x, minus this corner x that we cut out. And for the width, we're going to have 20 minus 2x. So again, 20, the length we started with, minus 2x, these lengths that we cut out from each corner. Also, when we think about what we cut out of these corners, well, if we cut out a side length of 10, we'd take the whole thing out. So this x value has to be less than 10, less than half the length, for there to be anything left for a base. So the domain for x, the amount we can cut out of the box, is going to be, it's got to be greater than 0. 20 minus 2x has to be greater than 0, which is going to make, if you add 2x, 20 greater than 2x, and 10 greater than x. So our volume, or this height, is going to be less than 10. Okay, so we have a domain for our function. Now what we've done in the past is we've taken and created these volume functions, and we've maximized them by simply graphing. If you think about just putting this function into our calculator, we've graphed it and calculated the maximum volume. If we cut out, what do we need to cut out for x? Well, now we're solving it analytically. So the first thing we need to do is simplify this. So notice I multiplied both of these terms by x, and then I FOILed these two terms and rearranged my volume function to get 4x cubed minus 90x squared plus 500x. Now this and this should be equivalent functions. So notice what I did here on my calculator is I've got the original function and then my simplified version, and what I'm going to do is I'm going to graph it, because if I graph it, if it just graphs over the top of the one function, I did it right. If I see two different graphs, I know I simplified wrong. So we're graphing along here, and it does work out that it's the same function. And I could check if I come down here, I can look at my table also, and notice we've got the same output for both functions for the same input. So I know I simplified it right. Now, if I want to know what that max volume is, what that length I'm going to cut out of each corner is, I can calculate the max. That's what we've done before. And I know that to get the maximum volume, I would cut out a corner of 3.681 inches. But I want you to show it to me analytically. How do we do that? So we take the derivative. 12, 3 times 4 is 12, x squared minus 2 times 90 is 180x plus 500, using the power rule, and we set that equal to 0. And when we do, well, that's not going to factor very nicely, so I'm going to go right to the quadratic formula. A equals 12, b equals negative 180, c equals 500. Easy enough to do, and on occasion you will do that. Okay? So x equals the opposite of b, so the opposite of 180, negative 180 plus or minus the square root, negative 180 squared minus 4 times 12 times 500, a times c, all over 2a. Well, when you put this in the calculator and square root it, you get 91.652. So if you got 180 plus that, and then you divide it by 24, we get 11.319. Nice, but not in our domain. So let's just cross it out. if we take 180 minus 91.652 and then divide that by 24, we'll get 3.681. Notice it is exactly what we got when we calculated the max. So we know we did that right. But you know that when we're doing this analytically, we're doing it without a calculator, without the benefit of graphs. So to verify that, we take the second derivative of this. And so we'd have 24x minus 180. And we have to evaluate it at 3.681. When I do that, well, 24 times, I'll just round it up to 4 to be generous. 24 times 4, 48, 96, minus 180, it's going to be a negative number. I don't care what the negative number is. I just know that then if it is negative, by the second derivative test, the volume function is concave down, which we saw graphically, and that's going to make a maximum value right here at 3.681 by the second derivative test. And you do have to say that when you're using this optimization process. So you say it's a max volume by the second derivative test. Now, to interpret that, I would take and I would store my value as A, and then I know that's the height of my function. Well, the width is going to be 20 minus 2 times A, and that's where I get my 12.638 inches, and the length is 25 minus 2 times A, and that's where I'm going to get my 17.638 inches. Now, the question asks for how large the square should be, and then what's the max volume. Well, you know that to do this, we never round until the end, so my max volume is going to be length times width, 20 minus 2A, times height, well, length times width times height, 25 minus 2A. So our maximum volume will be found at 820.528 cubic inches. And we would say that. So the maximum volume for the given length times width times height is this when the height equals 3.681 inches. So that's how we would do this. And we could do it all without benefit of the calculator, but I wanted you to see it back and forth with us. Now, if we're going to design a can, same process, but a little bit different. Because we have a different situation. You've been asked to design a 1-liter oil can shaped like a right circular cylinder. What dimensions will use the least amount of material? So that means what we need to find is we need to minimize surface area. Use least material, minimize surface area. Well, we're given a constraint. We know the volume of the can, if it's a liter, is 1,000 cubic centimeters. So I can write, I know volume is base times height. Well, the base of the can is a circle, so pi r squared times the height. And my constraint would be 1,000 equals pi r squared times the height. My surface area, I always kind of just sketch out a little net to see that. Well, I've got two circles for the top and the bottom. They're each going to have an area of pi r squared. And this rectangle that goes around the cylinder is going to be 2 pi r, the circumference here, times the height. So 2 pi r times h. So my surface area formula is here. Well, if I use this constraint, I can get all of this, solve it for h, to get the height is 1,000 over pi r squared, just by dividing here. And then I can substitute that into this formula. When I substitute it into my surface area formula, I can simplify it. The pi's will cancel out, and 1 r will cancel out. And I'm left with a surface area formula of 2 pi r squared plus 2,000, 2 times 1,000 here, times the radius to the negative 1 power, because it's just easier to use the power rule that way. Well, take my derivative, set it equal to 0. So take my derivative, 4 pi r plus, and I'm going to bring this negative exponent, so negative 2,000 times the radius to the negative 2, which I'll write as 2,000 over r squared. since I need a common denominator to find out where this equals 0, I'm going to have to multiply this by r squared over r squared, which is going to give me 4 pi r cubed over r squared minus 2,000 over r squared. And this, that leaves me with this for the derivative of my surface area, 4 pi r cubed minus 2,000 over r squared. Well, when this does not exist, the radius is 0. Well, if the radius is 0, the can doesn't exist, so I'm not going to worry about that particular radius. And I'm going to set my numerator equal to 0, 4 pi r cubed minus 2,000. Okay? If I do that, I'm going to set that equal to 0. I'm going to add 2,000 to both sides, divide by 4 pi, and cube root my answer. And when I do, I'm going to just pop that into my calculator, 2,000 divided by 4 pi, take the cube root, and I will get a radius of 5.419 centimeters. Now I need to know if that's going to be a max or a min, so I take the second derivative. And I'm going to come over here and get this first derivative that's set up so nice so I can use my power rule. And I would take the derivative of this. I'll get 4 pi, negative 2 times negative 1, so plus 4,000 r to the negative third. So there's my second derivative. I plug in 5.419 here, and I can see it's going to be positive. If it's positive, my surface area function is concave down, concave up there by the second derivative test, and this is going to be a minimum, which is cool because I was looking to minimize surface area. So I would say by the second derivative test, this is a minimum. That's my justification for this. So when I interpret it, what does it mean? It means I have a minimum value for surface area when the radius is 5.419 centimeters. The height, come up here to our height constraint, is going to be 1,000 divided by pi times 5.419. This, of course, was a stored value in my calculator to get 10.840 centimeters. And my surface area then, when I plug that into my surface area formula, is 2 pi times this radius squared plus 2 pi times this radius times the height. Again, I never round till the end. I use the stored values. So my minimum surface area would be 403.104 cubic centimeters when the radius is 5.419 centimeters and the height is 10.840. So our process every time: understand the problem, write your two equations, put them together, analyze the equation to be maximized or minimized, verify it using the first or second derivative test, and then interpret your answers. So hopefully this will help, and see you in class.